Hello friends, welcome to the Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created several playlists to cover various categories of problems dealing with stacks, queues, linked list, and also programming paradigms such as dynamic programming, greedy method, DFS, BFS, and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from the description section of this video below. Let's jump into today's problem. Search in a binary search tree. Given the root node of a binary search tree and a value, you need to find the node in the BST that the node's value equals to the given value. Return the subtree rooted with that node. If such node doesn't exist, you should return null. So basically we are given with a binary search tree and we are asked to find whether a particular value is there in that particular binary search tree or not. So if it is there, we should return the subtree which is rooted with that particular value. If it doesn't exist, we should just simply return null. That means an empty binary tree basically, right? So what we are given with an example here is we are given with a binary search tree 47213, right, and we are asked to search for 2. So we are able to find that, and the ask is it's not just true or false, but we are supposed to return the rooted subtree, right? So we return 2. So that includes the left and right subtrees of the root, the node with 2 as the root, right? So if we were to search, let's say 10 in this particular subtree, right, binary search tree, so 10 is not existing. For that you need to return null, right? So one thing that we have to understand is, it is given as binary search tree. So binary search tree has a specific property, so that if we know, then the problem will be easy for us to solve. So binary search tree, one of the main properties or one of the properties of the binary search tree is the left value in the binary search tree will be less than the root value, and root value is less than the right value. So this will be there, and at every level or every node of the binary search tree. Okay, so basically what we are saying is it's not just the left value alone or right value alone, but what we will say is the left subtree. Instead of we saying left value, right, let's say left subtree, right, left subtree values, right, should be less than the root dot value and right subtree values. So that's what we will say, instead of just right dot value, left dot value, right, because that will be more clear possibly, right? So all the subtrees, all the values in the left subtree should be less than the root value, and all the values in the right subtree should be greater than the root value. That's what it is, right? So, and this sub property will be holding true at every node in the tree. So that is the core property for a given binary search tree. So if we know this, right, so we don't have to really search for all the nodes into that particular binary tree, right? So now let's go back to the example. So given tree and search for, let's say search for 2, let's say, right? And in that particular case, what we do is, so 2 we compare with the root node, right? So 4 is there, so 2 is less than 4. So right, so search 2, let's say this is 2 is less than 4. That means we will going towards the left subtree, right? If we were to say, let's say search for 10, let's say, right, in that particular case, so root is 4 and we are searching for 10. That means from this property what we can easily say is, okay, it will be on the right subtree. We don't know whether it exists, the 10 exists, but it should be, if at all it exists, it should be there on the right subtree of 4, right, because root value will be less than the right subtree value, right? So root value is 4, so 10 is obviously greater than 4. That means 4 is less than 10. So this property satisfies, right? So that means since the root value is 4, the 10 should be onto the right subtree, right? So that's what the intention that we are going to use. So simply by using this method, right? So if I divide this into two things, right? So let's say root dot value. So these are the two conditions. So first condition and second condition. Let's say these are essentially same. I just divided into like two different things. That's it, right? So now that we know this is the property that a binary search tree has to follow, right? Let's go try to look at the code and understand the algorithm, right? So if root is null, whatever the tree that is passed to null, right, we just have to return null. It doesn't matter what value that it got passed to, right? So we just return null straight away. We don't have to do anything. But what if root dot value itself is the value? Just return the root. That's it. We are good. So if the value in this particular example we are searching for 4, right? So the very first node that we look at is the root node. It is 4. That's it. Return the root. But now we are into these two conditions. If it matches, we just return. But if it doesn't match, what happens, right? If this is what left subtree is less than root value, right? So now we are comparing this search value with the root. So if root value is less than the search value, right? So whatever the value that we are searching is greater than the root value. That means we have to go on to the right subtree, right? So this is what its condition is. So we are searching in the right subtree, right? So otherwise we search in the left subtree. That's it. So that is the simple code that we can look for, right? So basically what we are trying to do here is to search or minimize the search into whether go to the left side or right side, right? So this is almost similar to the binary search, right? Although we are not exactly dividing that search space into half, right? So let's say if we are searching for 7, right, then we just check with 4 and then decide whether we are going to the right or left, right? So we go right, that is 7. When we are here, we are already here and we are able to say okay, 7 is existing in it, right? So if it not exists, we just return null. So for the example of this, right, so since we are going through left and right subtrees here in a recursive manner, right, so search BST is calling itself. Basically it is doing the recursive search, so it will be done through the recursion method, right? So now let's go ahead and look at the time and space complexity, right? Time and space. So we observe that there is similarity between this search whatever we are doing and a binary search, right? So at the most how many elements that we are trying to look for, it depends on the number of levels in the binary tree, right? So if the number of levels in the binary tree is, let's say, L, right? L is number of levels in binary tree, right? So we will say okay, at each comparison we are taking a decision whether we need to go left side or right side. So that means the order of L is what the time complexity is. So that means the number of levels in the binary tree. So that is order of L, right? So that is the time complexity we are going to say for this particular problem, right? Let's look at the space complexity. So are we using any extra space here? So if you look at this code, right, nowhere we are using any extra space. So that means we will say okay, 0 space or maybe constant space. If you assume the recursive approach, right, basically it will use the recursion stack in by default, right? So for that purpose we can say okay, it is going to use the constant space because the number of calls that we are going to make is L. So if you want to call really the space also order of L, that shouldn't really harm, but explicitly we are not using any space. So for that I am saying it will be constant time complexity, right? So that is for this problem. We are able to solve this problem with the recursion method by using the property of binary search tree. If you have any further questions, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted this code to the GitHub repository. You can find the link in the description section of this video. If you haven't subscribe to the channel, please go ahead and subscribe and share among your friends as much as you can. Please click on the bell icon so that you will be notified about my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.